We've already learned how to compute average rate of change on a definite interval. That's from one point to another. Today we're going to talk about how to extend that to include an indefinite interval. That means a window that hasn't even been clearly defined yet. It doesn't have a clear beginning or a clear end. We're going to kind of do this by building off of understanding what it looks like to do it for a definite interval first. So we know that average rate of change from A to B is just f of B, the output of my final point, minus f of A, the output of my starting point, over B, my final point, minus A, my initial point. So what this looks like for 1 to 3 for this function is pretty straightforward. I'm going to have to find f of my initial point, f of 1, which in this case I can actually do in my head, but I'll write it out. 1 squared minus 5 times 1. 1 squared is 1. 5 times 1 is 5. 1 minus 5 is negative 4. And then f of 3, that other point, I can't do this in my head. 3 squared minus 5 times 3. 3 squared is 9. 5 times 3 is 15. That comes out 9 minus 15, a negative 6. So my average rate of change from 1 to 3 would be my final output, negative 6, minus my initial output, negative 4, all over my final 3 minus my initial 1. This, subtracting a negative number, is the same as adding a positive number, so I get negative 6 plus 4 over 3 minus 1 is 2. That comes out to negative 2 over 2, which means my average rate of change over this interval is a negative 1. If we were to graph this on Desmos, we would see that between those 2 points, it's declining on average, rise of negative 1 over run of 1. We can do the same thing for points that haven't even been picked yet. X and x plus h can represent any 2 points on an entire plane. And so this x coordinate right here is some number, and then this other x coordinate is some other number. And h is the magical thing that lets us relate them, because h tells us exactly how far apart these 2 x coordinates are from one another. Meaning that if we start at x and move a distance of h units over, then we will have our final point, x plus h. If this looks familiar to you from difference notation, that's because it's exactly what it is. And what we're doing now is using difference notation to compute the difference quotient. So we're going to use this same idea and plug this in over here. It's going to get a little bit messier, and that's okay. I'm not scared. I need to compute my initial output, and that's actually kind of already been done for me. If I plug in x, that's how the function was defined in the first place. So that's super easy. This next part, a little bit trickier. F of x plus h is equal to, well, over here, we take this x and we plug it in everywhere we see an x. And so what that means is that I will have x plus h squared minus 5 times x plus h. If you don't know how to distribute this and simplify this, you should take a moment, pause the video, and do it yourself in your notebook. Otherwise, I can actually do this in my head. X plus h squared is going to be x squared plus 2x h plus h squared minus, distribute the negative 5 as negative 5x and negative 5h. So what this now means is that I have finally figured out all the pieces that I need, but I still need to fit them into this puzzle. My final output is right here. Ouch, my red marker is dying. And my final input, my initial output, check it out, right there. So I will plug these things in exactly where my coloration implies that I would. The average rate of change from any point x to any other point x plus h is going to be equal to my final, which is x squared plus 2xh plus h squared minus 5x minus 5h minus the entire initial output, x squared minus 5x, all over my final input minus my initial input. This looks messy, and it's because it is pretty messy. But check out what happens. Some really magical stuff is about to occur. I'm going to simplify some of this. I have a negative, like minus this entire binomial. That's difficult for me to do in my head. So instead, I'm going to distribute out that negative sign. A negative 1 times an x is going to be negative x squared. And this negative 1 times this negative 5x is going to be a positive. So I can distribute out the negative sign like that. That's going to save me a lot of time. But this is where it gets cool. There's a negative x squared. And there's also a positive x squared. There's a positive 5x, and there's also a negative 5x. And there's a positive x and a negative x. So there are all of these like terms, which are eliminating each other. Moving one step further, my next line of this equation is going to say 2xh plus h squared minus 5h all over h. This is where I get fired up. Each of these terms has an h in it. So I can factor and cancel and get this even simpler than it is right now. The factored version of this would have an h out front times, there's a 2x left from the first term, h squared with one h factored out just goes down to h. Negative 5h with an h factored out goes down to just negative 5, all over h. And then, because I've factored, now I can cancel, which means that my average rate of change is 2x plus h minus 5 for any 2 points.